Yeah, welcome everybody. I would like to recall where we stopped last time. We had proposition 3.12. Which I would like to recall. We had let H0 be the minus Laplace operator, which we usually define on CC infinity. Here we are in R3, and then we take the closure to obtain a self-adjoint extension of this object. We take a potential in L2, which should also be bounded. And then we defined the operator H, which was H0 plus the potential, again a self-adjoint operator. And we claimed that then H0 is purely absolutely continuous. Is purely absolutely continuous. This means that the absolutely continuous subspace of H with respect to H0 is the Hilbert space. And furthermore, we claim that the wave operators exist. And the wave operators omega plus minus H0, which we defined as the strong limit for t going to plus or minus infinity, exponential IT H exponential minus IT H0, and then we usually had the projection onto the absolutely continuous subspace with respect to H0, but in this case this projection is equal to the identity according to this statement here. So we simply have this strong limit here, and we claim that the wave operators exist. Today I would like to work out a proof of this, and then we will proceed with the so-called Cook-Huck theorem. This will be our task for today. So let's have a look at a proof of this statement here. And to prepare this, we need a lemma, which is lemma 3.14. And it reads as follows. Here we need the free propagator, the so-called free propagator, which is exponential of minus IT H0 in R3. Here we claim it possesses a weak integral kernel, so possesses a weak integral kernel, which I denote by K. Kt. It depends on two variables, x and y, and it is defined by 1 over 4 pi it to the power of 3 over 2 times exponential minus absolute value x minus y to the power of 2 over 4 pi it. For x and y in R3, of course, and t non-zero, in the following sense, in the sense that exponential minus it H0 applied to an element f in the Hilbert space as a function of x. This is then given by the L2 limit, r going to infinity, 1 over 4 pi it to the power of 3/2 integral over the open ball with radius r, and then this exponential function here minus absolute value of x minus y to the power of 2 over 4 pi it f of y dy almost everywhere for any f in L2. Yeah, so we have here this so-called free propagator, which is this object here, and we claim that it can be represented by a weak integral kernel kt of this type, so that we have the following representation here for any f in the Hilbert space. And the proof of this is an exercise for you. So the proof is on the exercise sheet for today. So I leave it to you to go through this. The proof is not very difficult, but yeah, I think you can do it on your own. Let's continue. On the other blackboard. Okay, let's continue here. Following a remark, we will only apply this lemma for functions in CC infinity. And it is clear that in this case we do not need the L2 limit, where we do not need the L2 limit. Okay, we have the following corollary. It's corollary 3.15, and it reads as follows: for t non-zero, we claim that exponential minus it h0 maps the space L1 L1 of R3 continuously to L infinity of R3, and furthermore we have the estimate and the norm of exponential minus I th0u. The infinity norm is or can be estimated by some constant divided by t to the power of 3 over 2 times the norm of u in L1. And this holds then for any u in CC infinity of R3. Okay, let's have a look at the proof of this statement. Proof for u in CC infinity of R3. We know from our last lemma that we have the representation formula that exponential minus ith0 applied to u as a function of x is given by the following representation. With this integral kernel that we had on the other blackboard. Yeah, this is what we know, and then we can simply estimate, hence, we find that the infinity norm of this object this is by the definition nothing but the supremum for x in R3 of the absolute value of this here. As a function of x, of course. Yeah, and now we use the representation that we have to obtain that this can be estimated by 1 over 4 pi t to the power of 3/2 integral over R3. And here we simply have the absolute value of u of y dy, and then this can be estimated by some constant divided by t to the power of 3/2, and here we have remaining the L1 norm of u. And this is already the desired result. And you see that it simply follows from this representation formula. Okay, and now using these results, we can come to a proof of proposition 3.12. It is now very easy. Proof of proposition 3.12. And our goal here is to apply Cook's theorem that we had last week. So we apply Cook's theorem. And you might recall that we had a certain dense subspace, script D, which we have to define in a suitable way. And here I choose CC infinity of R3. Yeah? And maybe you recall that the essential thing that we had to assume in Cook's theorem was that the following integral was finite. Let's recall this. We had there two self-adjoint operators, B and A, and then we had this condition here. This integral with respect to t has to be finite for any phi in this space D. And in our situation, we now define D to be this CC infinity space here, and we have the operators A and B in the following way. Our operator B is simply H0, a self-adjoint extension of minus Laplace, and we have A. In our case, this is the Schrödinger operator H0 plus potential. Yeah, and then you see what the difference is. Actually, it's the potential here that's remaining, and here we have kind of free propagator remaining. Yeah, so we can use the lemma that we had prepared in advance, and yeah, we can simply estimate now in the following way. So this was to recall the assumption of Cook's theorem. So now for u, in CC infinity of R3, we have that. Now we simply write down this object here that we have to estimate. So the integrand, basically, it's norm of potential times exponential minus IT H0U. Yeah, I hope you can identify that this term here is exactly the integrand in our case. Yeah? As I explained here, this difference B minus A basically is the potential, because the H0 cancels out. And when we replace B here by H0, we simply have this propagator term. Yeah? And D is our dense subspace CC infinity, so we choose a function U in this space, and we consider this term. That's why I'm interested in this object here. Okay, let's estimate this. We can estimate it by the L2 norm of the potential times the supremum norm of the propagator term. Yeah, simply by considering the definition of this L2 norm. Then this is clear. And now we can use our lemma, which says that we can estimate the right-hand side by constant divided by t to the power of 3 over 2. Here we have the norm of the potential times the L1 norm of the function u. Yeah, but we know the function t is sent to t to the power of minus 3 over 2. This, of course, is integrable at plus or minus infinity. So that the condition and 3.4, this is exactly here this integral formula, so that the condition 3.4 in Cook's theorem is satisfied. And then, of course, we can apply the theorem, and our result is a direct consequence of Cook's theorem. Okay. Let's consider potentials that may enter the game. So suppose that, for example, the potential may be estimated in the following way. Potential is bounded by some constant times 1 plus the absolute value of x to the power of minus beta for x in R3. Yeah, why do we look at this? Yeah, if this exponent beta, so if beta is larger than 3 over 2, then the potential is in L2. Yeah? Do you see this? If beta is larger than 3 over 2, then this object is in L2. Is it clear? Yeah, because we have to use polar coordinates, and then we have in the denominator 1 plus r to the power of 3 over 2, but in polar coordinates you also have to integrate r to the power of 2. Yeah, this is an additional term, and then this integral will be finite. So that's why we need this assumption here. So as the integral from 0 to infinity over r to the power of 2, which is an additional factor when we introduce polar coordinates, and here in the denominator 1 plus r, and to the power of 2 beta, because we are interested in the L2 case, dr, this will then be finite, if we assume that beta is larger than 3 over 2. Okay, but an interesting remark by a suitable choice of the space D. I will not go into details here, but it's interesting to remark this. The result of proposition 3.12 can be improved. Regarding the case beta bigger than 1. Yeah, but again, and we had also seen this in our introductory lectures, we cannot really handle the Coulomb case with this approach. Yeah, we only have beta bigger than 1, so this is important to keep in mind. Nevertheless, it's possible to improve the result that I had presented so far when we change the setting and choose a different space D. Okay, today in my lecture I would like to discuss in detail the following theorem. It's theorem 3.16, and it's the Cook-Huck theorem. And it reads as follows. Let V be a potential in L2 of R3 plus LR of R3 for some R that's in the interval from 2 to 3, where we allow the right boundary 3 and the 2 is excluded, and assume in addition and let V be bounded. Yeah, then again let H0 be the minus Laplace operator as a self-adjoint object in the Hilbert space of course in the L2 space, and let again H be the Schrödinger operator H0 plus the potential, and then I claim that the wave operators exist. Yeah, so then the wave operators omega plus minus for the pair H0 exist. Yeah, and I would like to take the rest of our time for today to present in detail the proof of this important theorem. And I have subdivided this proof into several steps so that it is easier to follow the arguments. So, proof. And I also have to say that some steps of the proof are kind of exercise for you, so that the presentation can be can be able to be done in one lecture. So some elementary steps are sourced out as an exercise for you. Okay, let's start. For gamma positive, we consider the following functions. We consider the functions phi gamma of x, which I define as gamma to the power of 3 over 4 times exponential minus gamma absolute value of x to the power of 2 divided by 2 for x in R3. And I define the following space and define the space D, which should be the linear span of the translates of these functions in the following sense. Yeah, I take vectors in R3, and then I consider this translate here of the function phi gamma that I had defined here, and I do this for values gamma positive and a in R3, and then I consider the linear span of these objects. And then I claim, and this is then an exercise for you to prove this. Let's do it here. Then I claim that then the space D is first of all a subset of the domain of H0, which is under our assumptions equal to the domain of H. And furthermore, when I take the closure of this span of this space D, I get the Hilbert space H. Yeah, and the proof is left as an exercise. So see exercise 12. Okay, and we will work with these functions phi gamma in the following. And first of all, we show this result here, step 1. We first show that exponential minus it h0 applied to phi gamma as a function of x. This has the following form. Here we have a function alpha of t to the power of 3 over 4 exponential minus 1/2 alpha of t plus I beta of t times x absolute value of x to the power of 2. Furthermore, we have a formula for the alpha where alpha of t is given by, or is defined by, gamma divided by 1 plus 4 t square gamma square for t non-negative. And the beta is not really interesting, but let's state it here, where alpha is this and beta is a function from R to R. I've simply written, is not interesting, and beta is not interesting, as you will see. Yeah, but we have such a representation. This is important. Yeah, let's give a number for this. Let's say it's 3.7. Yeah, and now I would like to prove this representation. So to prove To prove 3.7, we make use of the fact that as you all know, that the Fourier transform applied to phi gamma, this is then a function of a variable k, and I will in the following also denote this as phi gamma hat of k, that this is of the form c gamma with a constant c depending on gamma times exponential minus absolute value of k divided by 2 gamma for k in R3. Okay. With suitable numbers c gamma, so with suitable numbers c gamma, and this is also an exercise. Exercise 11. Yeah, I think you all know this result, and I'm sure that you all know the proof, but it's a nice technical training to go through the computation once more. So this is left as an exercise on the sheet for today. Yeah, and to have it complete, let's state also this here. The operator f denotes, of course, the Fourier transform. You all know that it is possible to define this in L2, given by, as you know, Fourier transform of phi as a function of k, or also denoted as phi hat of k. This is nothing but the L2 limit. This is the L2 limit, r going to infinity 1 over 2 pi to the power of 3 over 2, integral over the ball with radius r, exponential minus I k times x, phi of x dx, of course, for phi in L2. And you also know that, let us state this for the sake of completeness, you also know that the operator f is unitary. And its inverse is given by f to the power of minus 1 applied to a function psi of x, and this is then also the adjoint operator f star, and it's given by, as you all know, the L2 limit for r going to infinity 1 over 2 pi to the power of 3 over 2, integral over the ball with radius r, exponential I, k times x, psi of k, dk. And now the interesting thing is that the Fourier transform, it allows for a functional calculus the Fourier transform allows for a functional calculus for the Laplace operator precisely. We have that h0 is nothing but multiplication with the absolute value of k to the power of 2, but under the unitary transformation that is given by the Fourier transform. And then it's clear that exponential minus I th0 is then nothing but f to the power of minus 1 multiplication operator for the function exponential minus it absolute value of k to the power of 2, and then again the Fourier transform. Okay, now let's use this, and then we infer that the following statement is true. The Fourier transform of exponential minus it h0 applied to phi gamma. What is this? Yeah, now we make use of this formula here. You simply have to apply the operator f to this equation here, yeah, to this right equation here, and then you find that this is nothing but the complex number exponential minus it absolute value of k to the power of 2 times the Fourier transform of phi gamma of k. Yeah? And then we use this exercise, which tells us how this Fourier transform here looks like, so that we find that this equals C gamma exponential of minus absolute value of k to the power of 2 it plus 1 over 2 gamma. And I would like to rewrite this in the following way. I would like to introduce the following notation. This is exponential minus absolute value of k to the power of 2 divided by 2 gamma of t, and this gamma of t is introduced in the following sense. Gamma of t should be gamma to the power of minus 1 plus 2 it to the power of minus 1. Yeah, if you use this definition, then you see that these equalities are true here. Yeah, then you see that you get from here to here. So this is simply a different way to represent this result here. Yeah, but then, hence, we find that the exponential of minus ith0, this is the object here, yeah, of course applied to phi gamma. How do we get it, or where do we get it from? We simply have to apply the inverse Fourier transform to this equation. Then here we get the object that we want, and here we have to compute the inverse Fourier transform of this right-hand side, but that's possible because we know how this exponential term behaves. This is the exercise. Yeah? So we can directly write down the result. Hence this here is given by the inverse Fourier transform applied to C gamma exponential minus absolute value of k to the power of 2 divided by 2 gamma of t. This simply is the right-hand side here. Yeah, but this is, according to our exercise, then C gamma, C 1 over gamma of t exponential minus gamma of t divided by 2 absolute value of x to the power of 2. You simply have to apply this exercise, I think 11, yeah, it's on your exercise sheet, the first exercise, to obtain that we have this formula here. And in the following, I will, in order to simplify the notation, I will write for this factor here, C gamma of t twiddle. Yeah, and our next task, as you might know, is that we will compute the real and the imaginary part of this gamma, because we are interested of the decomposition here in the exponent, and then we have to verify that the factor here is indeed as we want to. Yeah, this will be the next step. So let me now clean the blackboards, and then we will continue with this computation. And now let's continue with the computation of the gamma. So let us compute the real and imaginary part of this function gamma of t that we had in the exponent. And yeah, this is of course easy. Gamma of t, by our definition, is 1 over gamma plus 2it, and this can be rewritten in the sense that it's gamma to the power of -1 minus 2it divided by gamma to the power of -2 plus 4 times t squared, and then we find that this is nothing but gamma divided by 1 plus 4t to the power of 2 gamma to the power of 2 plus I times minus 2t divided by gamma to the power of -2 plus 4t to the power of 2. Yeah, and of course, this here is now my alpha. When we think of the formula 3.7, and this is then beta of t. Yeah, but what about this constant c twiddle gamma of t that I had introduced on the other blackboard? Let's comment on how to compute this. This is possible. Yeah, as the exponential group has exponential minus it h0 as a map h to h is unitary, we obtain the constant. C twiddle gamma of t simply from the following condition. From the equation that the norm of exponential minus it h0 gamma phi is nothing but the norm of gamma, phi gamma in this way. Because of the fact that this operator is unitary. This is what we can use. Yeah, and then we simply have to compute the left and right hand side. So where we have that, the norm of phi gamma, this is nothing but gamma to the power of 3 over 2 times the integral over r exponential minus gamma, and here we have the absolute value of x to the power of 2. Of course, this is the square of this object, dx. Yeah, simply of the definition of this function. Yeah, but then I can use a change of variables to rewrite this in the form that it is nothing but integral over r exponential minus absolute value of x to the power of 2 dx. And we have that the norm of exponential minus it h0 phi gamma to the power of 2. What is this? Here we have this constant that we are interested in, c gamma twiddle of t to the power of 2, integral over r, exponential now minus alpha of t, absolute value of x, to the power of 2 dx. Of course, the imaginary part now drops out, yeah, because we are taking the absolute value, yeah, when computing the L2 norm. So this is what we have remaining, and then again a change of variables leads to the representation c gamma twiddle to the power of 2 of t, alpha of t to the power of minus 3 over 2, and here we have the integral over r exponential minus absolute value of x to the power of 2 dx. Yeah, and then clearly, so that we find that c gamma twiddle to the power of 2 of t, alpha of t to the power of 3 divided by 2 must be equal to 1. Yeah, simply from comparing these two terms here. Yeah, these both are equal, so this object drops out, and then this coefficient here has to be equal to 1. Yeah, but then we find that this is nothing but the representation that the c gamma of t twiddle is nothing but alpha of t to the power of 3 over 4. And taking everything together now, this achieves a proof of 3.7. Which was our first step. Okay, then let's go on. Number 2. Step 2. I claim that using the formula 3.7, we obtain for m positive and large T, precisely T, absolute value bigger than 1 over gamma, the following bound. The bound that the norm of 1 plus absolute value of x to the power of m exponential minus it h0 phi gamma in the infinity norm, this can be bounded by some constant c of gamma times 1 plus absolute value of t to the power of m minus 3/2. This is what I would like to prove now. How do we get this? Now this follows from the following observation. So let's start with the left-hand side. The norm of 1 plus absolute value of x to the power of m exponential minus it h0 phi gamma in the infinity norm. This is according to 3.7 given by, or it can be estimated by the supremum for x in R3 taken over 1 plus absolute value of x to the power of m, alpha of t to the power of 3 over 4 exponential minus 1/2 alpha of t absolute value of x to the power of 2. We are simply using the formula 3.7 and what we had obtained in step 1. Okay, now I use the definition of the alpha that we had also in step 1 to conclude that we can estimate this right-hand side here by some constant, let's say C1, divided by 1 plus absolute value of t to the power of 3 over 2. And then we have the supremum for x in R3 of 1 plus absolute value of x to the power of m exponential minus 1/2 alpha of t times absolute value of x to the power of 2. Yeah, simply consider the definition of the alpha and then you get this factor with the t here. Okay, now let's go on. And the fact that for large t, precisely t bigger than 1 over gamma, we obtain the following. Let's change the blackboard, since we need more space. We obtain that. Yeah, first of all, I would like to introduce new variables. I would like to write x as y times t for, let's say, t positive. And then I get that the supremum for x in R3 of the absolute value of 1 plus x to the power of m exponential minus 1/2 alpha of t absolute value of x to the power of 2. Yeah, when you look back to the other blackboard, this was exactly where we stopped here. This is the object that we are interested in. And now we deal with the additional assumption that t is large, precisely larger than 1 over gamma. And here I introduce new variables, or precisely a new variable y, by this definition, so that we can do the following. This can then be estimated by the supremum for y in R3 then, absolute value of 1 plus t, absolute value of y to the power of n. And here I get exponential minus 1/2 alpha of t, t to the power of 2, absolute value of y to the power of 2. Yeah, and now let's take a little bit of time to discuss this exponent here. We have, so this is a kind of calculation here, we have alpha of t times t to the power of 2 here in the exponent, yeah, which comes from the change of variables. This is the object that I would like to discuss now. This is given by the definition of the alpha by 1 over gamma, gamma t to the power of 2 divided by 1 plus 4 gamma t to the power of 2. Yeah, in the definition of the alpha, originally we only have gamma in the exponent, but now I have written gamma to the power of 2 and 1 over gamma, so that 1 gamma will cancel out. And we have the factor t to the power of 2 that enters the game here. Do you see this? I've simply rewritten this expression. Yeah, but then you see that we have an auxiliary function, let's say h here, h, let's say, of psi, which is psi to the power of 2 divided by 1 plus 4 psi to the power of 2. And it's clear that this function is 0 for phi for psi equal to 0, and it goes to, for psi to infinity, to 1 over 4. So we can infer that this function will look like that. Yeah? This is the function h. And our condition that t is, the absolute value of t is larger than 1 over gamma, and of course we assume t is positive, means that in our case that gamma t is larger than or equal to 1. Yeah? So in consequence we find that the alpha t times t to the power of 2, this of course is then smaller than 1 over 4 gamma, because this gamma here is a factor that remains. And when we insert the value 1, we obtain 1 over 5. Yeah? So it looks like this. And let's go back here. Then we can estimate in the following way. We find that this can be estimated by the supremum. Hope you can read this. The supremum for y in R3. And then we get here absolute value of 1 plus t, absolute value of y to the power of m, exponential. Yeah. Yeah, you know, and now I use the smaller value to obtain a bigger value here on the right hand side, because it's exponential of minus this positive value here. So if I take the smaller value, I will obtain a bigger result. So I obtain here minus 1 over 10 gamma times y to the power of 2. Yeah? And then you see that this can be estimated by some constant, let's say C2, times absolute value of t to the power of m. This is then standard. Yeah, and when we look back to the other blackboard, we had here, up to a constant, the factor 1 plus t to the power of 3 over 2 in the denominator, and we have here on the other blackboard the factor t to the power of m, so that both estimates together show 3.8. Sorry, I think I have forgotten the number. Yeah. This is 3.8. So taking both results together. Okay, so it's nice to see it again. Both results together exactly yield this term. Yeah. So this proves 3.8. Okay, step 3. We now write the potential as V2 plus VR. Recall that the potential comes from the class L2 plus LR, so that we can write down such a decomposition and deduce that the norm of V times exponential minus I th0 phi gamma, this is the object which is interesting for us, and here I consider the L2 norm of this. This can then be estimated in the following way. Oh, sorry, I need new chalk. First of all, I add in a factor 1 to be able to decompose this in the following way. Norm of 1 plus absolute value of x to the power of minus m. This is the factor that is introduced, v2, v in the norm of, in the L2 norm, like this, times the norm of 1 plus absolute value of x to the power of m exponential minus it h naught phi gamma in the L infinity norm. Yeah, so nothing has happened. I have simply added a factor 1 in the form that I have written times 1 plus absolute value of x to the power of minus m times 1 plus absolute value of x to the power of m. Yeah? And then I have decomposed in the usual way that I take the supremum of this object and I write it in front of the integral, and the rest that is remaining is this L2 norm here. So let's go on. This can be decomposed in the following way. Now I use that V is the sum V2 plus VR to be able to estimate in the following way. I have the norm of 1 plus absolute value of x to the power of minus m times V2, and this is in the L2 norm, and then plus the norm of 1 plus absolute value of x to the power of minus m, VR in the L2 norm again. This is, simply a consequence of the fact that the V is the sum here, and then I can, by the triangle inequality, decompose in this way. And here I used our result that we already had obtained to write it as, or to estimate it as C of gamma, 1 plus t, or absolute value of t, to the power of m minus 3 over 2. Yeah, this is where we are. And now let's go on here. This object can then be estimated by another constant, let's say C prime of gamma, times, first of all, let me write it down, norm of V2 in the L2 norm plus the norm of VR in the LR norm times 1 plus t to the power of m minus 3 over 2. So this factor here is clear. We obtain a new constant, so we only have to understand where this factor here comes from. First of all, I have to again add that this holds true for all m in the interval from 0 to 1/2. Yeah, why is this true? Let me explain this. Here we have used, first of all, the trivial estimate. That the norm of 1 plus absolute value of x to the power of minus m v2, as this factor here is always smaller than or equal to 1. So we can estimate this L2 norm simply by the L2 norm of the V2. And in addition, the fact that the norm of 1 plus absolute value of x to the power of minus m VR in the L2 norm. Now when you look back to the other blackboard, you see that this is the second term here. Yeah, we had the trivial estimate for the first term, and concerning the second term, we can do the following. This can be estimated by the norm of 1 plus the function that sends x to the absolute value of x to the power of minus m, and this in the LS norm times the r in the LR norm, and we can do this provided we have that 1 over 2, this is the index from the L2 norm, is equal to 1 over r plus 1 over s. And now keep in mind that r, also let's say as r, is in the interval from 2 to 3. This defines some s bigger than 6, so that this estimate here works. Yeah? And then we choose, so we now choose m in the interval from 0 to 1/2 with the property that m times s is bigger than 3. Of course, this works when m is in this interval and s is bigger than 6, so that finally 1 plus absolute value of x to the power of m, or let's say this function here to make it more precise, that this is an element of LS of R3. Yeah, you take this to the power of s, and then you use the same argument with the polar coordinates that we already had, so that this works here. Yeah, because in polar coordinates, as I had already explained, we always get this additional factor r to the power of 2, yeah, from the transformation of the coordinates. And then when we have this representation and we have in the denominator r to the power of ms, which is bigger than 3, then this works. Then this is indeed in LS. So this is correct. Furthermore, in this setting, then m minus 3/2, which was always in our exponent, you recall this, is then smaller than minus 1. Now this is also clear. And we see that the norm of v exponential minus ith0 phi in the L2 norm, it should be phi here, this is correct, is integrable. This is integrable at t equal to plus or minus infinity for all phi in d, because d is the linear span of these functions phi gamma that we had so far. Yeah, and then we simply apply Cook's method, so we can say the desired result now follows from Cook's method. And then we are done here. Okay, to round it off, I would like to give 2 final remarks for today. Very short. First of all, 2 remarks under 3.17. So it's remark 3.17. First of all, the proof of theorem 3.16 shows that it is crucial to obtain estimates on propagator terms, so estimates on or for terms of the form exponential minus it h0 phi. Yeah, and I would like to remark that there is a more systematic way to obtain such estimates, a systematic method to produce such estimates is the so-called idea of stationary phase, And you should look up this in Reed Simon's book in the 3rd volume, where this is explained in detail. I can also give you the pages. So here you find it on the pages 37 until 46. Please look it up there. And finally, remark number 2. I also said that we have some difficulties with the Coulomb case, but this remark here is important. The Cook-Huck theorem enables to discuss potentials in R3, potentials in R3 that satisfy the following estimate, which is nice. Estimate V of x can be estimated by constant times 1 plus x to the power of minus 1 minus epsilon for x in R3. And of course, epsilon positive. Yeah, but nevertheless, we have, as you see, a problem with the Coulomb case. So let's state it here. Simple scattering theory. Simple scattering theory breaks down at the Coulomb potential. This is important to keep in mind. Nevertheless, of course, it's possible to handle the Coulomb case. You have to modify the whole setting. And again, for the Coulomb case and further details, I again refer to Reed Simon, volume 3, where you can find a lot of more stuff around this. Okay, this is the point where I would like to stop for today. Next week we will start with the so-called Cato-Burman theory, a new chapter. It deals with Schatten von Neumann classes and so on, but the details of this and what's the sense of this, I will explain it to you next week. So for today, I thank you very much, and we will continue with the exercises in a few minutes. Thanks.